Our speaker today is Mohsen Zaeem. He obtained his Bachelor of Science in Mechanical Engineering from Shiraz University in Iran, and then Master of Science, also in Mechanical Engineering, from the same institution. After which he obtained a PhD in Mechanical Engineering from Washington State University. And then he went to Mississippi State University, where he was a postdoctoral fellow, a lecturer, and then an assistant research professor in the institution. Since 2012, he's been an assistant professor at Missouri University of Science and Technology. And he's speaking today on predicting microstructures and properties of materials by phase field modeling. And I should point out that he's a faculty candidate for a position here in the engineering school. So please welcome Dr. Zaeem.
Thank you. Good afternoon, everyone, and thank you for coming to my presentation, and thank you for the introduction. So before I start actually my talk today, I wanted to thank my students, my graduate students, undergraduate researchers, and postdoctoral research associates that I'm going to mostly present their results to you today. Also, I want to thank my collaborators and funding agencies that have been funded my research for the last 6 years. So the outline of my talk, motivation, why we need to study nano and microstructures, and how we can use computational modeling in this area. Then I will talk about a brief introduction about phase field modeling, a model that we can apply to study nano and microstructures. I will show you examples of different phase field models. One series of examples for dendritic solidification of cubic and hexagonal lightweight materials, and another line of examples for oxidation, martensitic phase transformation, and hydrate precipitation in nuclear fuel cladding materials. So it's related to nuclear energy materials. At the end, I will briefly will talk about a new phase field model, which we call it phase field crystal, where we connect actually electronic structures, molecular dynamics, and phase field modeling to have a unique model that can capture lower scales, details, also work at a diffusive time and length scale. At the end, a short conclusion. So the first question is why we need to study nano and microstructures, and the simple answer to that is because they control the properties. They control mechanical, electrical, magnetic, optical, and other properties. So this is the short answer to this question. But if we want to study materials, we need to know that materials have different features at different length scales. If we start from the smallest scale possible, like electronic scale, so traditionally, if we wanted to study materials at electronic scale, we would have like physics department to do that for us. Or a little bit higher length scale, atomistic or molecular scale, chemistry, microstructure was actually material science, and macro scale, the properties in macro scale by engineering. But nowadays we have multidisciplinary research. If you want to get information from the macro scale properties, you need to know what is going on here, you need to know what is going on here. So that is the point. You need to have some kind of overview of different features of material, some kind of information on how you can actually connect the dots, okay? I put these four actually pictures here. In the left, you see 100 nanometer length scale. In the right, you see 1 millimeter length scale. These are different actually examples that I have been working on, different projects. I'm going to shortly actually explain this one and this one because of time limit, but the first one is the ultra-fine grain materials. That the average grain size is about 100 nanometer. The grain size here determines the overall strength of the material. Going to a little bit higher length scale, 2 microns. So these particles, these black particles, this superalloy is a nickel titanium superalloy to make turbine blades of jet engines. The size, shape, and volume fraction of these particles determine the rupture life of turbine blades. This particular example shows the architecture of a ultra-high temperature ceramic material we designed actually for thermal protection system of aerospace shuttles. So they go actually at very high temperatures when they want to go outside of the Earth or when they're coming back. So There are ceramics because they have very high melting temperature, but since they're ceramics, they have very low fracture toughness. So we wanted to design an architecture to increase the fracture toughness of those materials. And at the end, actually, you see a bioactive scaffold. You see 1 millimeter length scale. The scaffold here, the diameter of those filaments are about 300 nanometer. So application of this, bone replacement. So these examples shows you that materials have different features at different length scales. Those materials have could have completely different applications. But the important thing is how actually we can study these structures, how we can study these nano and macrostructure and connect it to properties. So let's go a little bit more deeper in these couple of examples, like nickel-based superalloys, as I mentioned in the previous lecture. So this is a new type jet engine for Boeing 787 or Dreamliner. And this is a cross-section of jet engine. The back of the jet engine is the most critical part because it goes to the highest temperature. So what is the material being used to make it? Nickel, titanium superalloys. But let's look at the macrostructure. Let's see how these small macrostructure control the rupture life. So jet engine, when in the takeoff, they can get to very critical temperature. And sometimes, actually, they will remain in that temperature, which is going to be a very critical situation. So let's assume that jet engine reaches 900 degrees Celsius, this black dots here. Okay. If we have used this nickel-based superalloy to make the turbine blade, the jet engine will only last 10 hours. So if you're in a flight going from Boston to Beijing, it's more than 10 hours, right? And this happens in the beginning. The pilot can monitor the temperature. So he has to land before reaching Beijing. But what if you produce this microstructure? You have 60% of these particles, which we call it gamma prime particles. It can last 1,000 hours. Okay, this is the effect of these small scale particles on the overall property of the jet. The overall jet engine will fail, actually, if you don't have the right material. So this is the first thing I want to say. The second thing is how we can go from here to here. That is the next question. We need to understand the mechanisms controlling nano and macrostructures. And for this example, actually, we produced and developed a model. It's a phase field model. What it gives us is the size, shape, and volume fraction of these particles based on the composition and heat treatment condition. Okay, so basically we can predict what is happening, and we can guide experimentalists and industry. So this was for that example. Let's go to the completely different example. This is bioactive material for bone replacement. So this is the bioactive glass scaffold. We call it bioactive because it can actually, the tissues can generate and go inside this bioactive glass scaffold. How we make this? We make this through one kind of additive manufacturing called SLM, selective laser melting. And basically, we can have a scaffold, like layers parallel to each other, and we have another layer coming with 90 degrees, okay? So these are really good. They are bioactive, biocompatible, but they are glasses. They can carry good compression, but they're not good in bending. You can break them much easier than metallic alloys. So, but they're really, really a much lower density than metal. So these are going to be much more favorable for bone replacement. So we wanted to do engineered architectures. So this is kind of a bio-inspired design. So if you look at a cross-section of a bone, it's a long bone at the cross-section. At the surfaces, you have high density. As you go to inside, you get more porosity. And in the middle, actually, you have a very big porosity. So based on this, we wanted to design an architecture that increases the flexural strength or bending strength. So what we did before actually doing trial and errors in our lab, we did computer simulation. Let me make it a little bit bigger. So this is what we have. This is the scaffold. We have long filaments designated by L, short filaments by S. So we can have different architectures, right? Let's mix it, run like 200 simulations. See which one actually will give us the best flexural strength. And we did that, actually. This is the assembly of 4-point bending. So we are bending the scaffold. And when you bend the scaffold, the bottom layer will go to tension, right? So we plotted the tension in the bottom layer versus different architectures. So L4S1 is this one, L4S1. Same amount of load that you apply will create the minimum tensile stress in the bottom layer of the scaffold. What does this mean? It means probably this architecture will have the highest flexural strength. So what we did, we reprogrammed our additive manufacturing machine. So it's a code, so you can, first in the computer, you can recode it, and then actually it will print different architectures for you. So this is the uniform one. This is the L4S1 structure, high density at the surface, low density in the middle. What are the results? These are the actual 4-point bending results. So this is the L1S1, the uniform. This is the L4S1. We increased the flexural strength 100%, twice. So the point I wanted to make here is computational modeling can be applied for different, study actually different materials at different length scales and for different applications. But we need to know what computational modeling are there, what data they can provide for us. So for that reason, I put this map here. This is a multi-scale modeling map. So basically, I put the smallest scale possible electronic structures. You can see, for example, simulate the building block of materials, like crystal structures. What are the position of atoms here? Okay? So this works only for 400, 500 atoms. Let's go a little bit higher length scale. Molecular dynamic simulations, you can go up to a couple of million atoms and simulate. Then you reach your length scale. It's like 10 nanometers to 500 micron. These are not going to work for you anymore because of the length scale limit and the time scale limit. The time scale of, for example, molecular dynamics is femtosecond. Okay? So here phenomena like phase transformation, crack propagation, grain boundary movement, everything happens here, which we call it mesoscale. And these are mesoscale models. So what I'm going to talk about today is a phase field modeling method applicable from 10 nanometers to 500 microns. So with this motivation and introduction, let's start the introduction to the phase field modeling. What is phase field modeling? How it works? So let's start with this example on the right side. So we have a matrix. We have two particles. It is high temperature. What happens? These two particles get together, necking, coarsening, right? We want to know how we can simulate this mathematically. There are two different ways to study moving boundaries or moving interfaces. One is the sharp interface model. The sharp interface model assumes that let's assume that we're studying, following the concentration of an alloying element in the domain. Concentration. Sharp interface model assumes that there is a sharp transition at the interface for our variable. So can you have a continuum equation for the whole system? The answer is no, because this jump will create singularity, right? So it means you need to have extra equations to represent interfaces. So let's assume that you have a three-dimensional system, many different interfaces. Each of those interfaces need to have its own equation. Phase field model, on the other hand, assumes there is a transition region. There is a mixture of atoms. So it is more physical, actually. If you look at a grain boundary, so you cannot say right side of this grain boundary we have one type atom, left side of the grain boundary we have another type. There is a mixture of atoms. So because of that, the concentration will not have this jump. It's going to go smoothly, and it will create a finite value for the gradient of this concentration, for example. So this is just one field concentration. We can have many other different fields. This is a phase field method. So we can have vacancy fields, we can have void fields, we can have actually some kind of fields for phase transformation showing like orientation or crystallinity. What are the governing equations we have? So we can have one governing equation for the whole domain, the first thing, or actually we can have coupled equations depending on how complex is our system. Basically, we can have second-order partial differential equations or fourth-order. You may be familiar with this fourth order. It is Kahn-Hilliard type equations. The second order is called Gibbs-Landau time-dependent equation. But most importantly, if we have a conserved field, we have a domain. The amount of material is in this domain doesn't change, okay, like the concentration of alloying elements. So it's a conserved field. So we have conservation of mass. So it will be fourth order. The second order usually used for solidification and melting. We have the same domain. Initially, it is liquid. All of that will become solid. So we do not have conservation of liquid, right? So it is non-conserved. So we can actually couple these two fields with solid mechanics equation and Navier-Stokes equation, depending if you want to study fluid mechanics, like immiscible fluid evolution, or solid-state phase transformation. So it could be coupled to others. What are the applications? There are many different applications, as I mentioned. You can simulate solidification structures or crystallization. You can simulate some kind of hydrate precipitates in different materials. This is particularly for zirconium nucleophile cladding. You can simulate phase transformation, which is very important in many different materials. And recently, different fields has been introduced to phase field model, dislocation dynamics, crack propagation, so we can have a crack field added to the phase field model, or some other things. So with this, I finished the introduction to phase field modeling, but let's go to a little bit more detail of some of the phase field models. The first series of examples are related to the dendritic solidification of lightweight materials. Why this is an important area? Why it is important actually to study solidification? Solidification happens in many different manufacturing processes. If you do casting, if you do welding, if you do laser additive manufacturing, in one step of your process, you are going to have material in liquid state, and it will become solid. So in casting, it is not very rapid solidification, but in laser additive manufacturing, it's a rapid solidification. So this is one example from one of my colleagues in Los Alamos National Lab and Amy Clark. So they have been working on in situ experiments looking at how the dendrites form and evolve in this lightweight aluminum copper. As you can see, these dendrites, so we call it this dendritic solidification. These dendrites actually determine the mechanical properties, the spacing between the dendrites, okay? Another example I wanted to show you here is magnesium alloys. So solidification of magnesium alloys. If you have bought a car after 2008 or 2010, some parts of your car are made by magnesium alloys. Why? Because magnesium alloys are 80% lighter than steel alloys, 33% lighter than aluminum alloys. So some of the steel alloys and aluminum alloys were replaced. Why? Because first, they're going to reduce the weight of your car, fuel efficient, more greener car. And magnesium alloy can have twice as aluminum alloy strength. So if you replace anything in the cars that were made by aluminum, now you make it by magnesium, you're going to increase the safety. So energy efficiency and safety, but how the microstructures control those? How the microstructure control the, for example, yield strength? I'm assuming that you know what yield strengths mean. If you do tensile testing, after some place that you do elastic deformation, it goes to plastic. So right before going to plastic, that is the yield point, okay? So this is the average actually size of these dendrites, okay, versus yield strength of this industrial grade magnesium, 9% aluminum, 1% zinc. If you look at this, if after casting we have average dendrite size of 1 micron, the yield strength is about 400 megapascal, almost twice as many aluminums. But what if you didn't control it well? What if your average dendrite structure is 100? Drops to 150 microns, like you just lost all your strengths, right? So it is important to know what features during solidification control what material. So let's go and start a model, how we can make a phase field model. So this is the simplest phase field model for solidification of pure materials, developed 1993. At the moment, Professor Kobayashi was a visitor in NIST in the United States, so they developed this model. And how the phase field model work? It is based on energy. If you can make an equation that represents all the energy in your domain, you can have a phase field model, okay? It's basically like you're riding your bike up the hill. When you reach up the hill, you're tired, but the bicycle has some kind of energy stored, right? Then when you go back, it's going to release that energy, so you don't need to make any energy. So it's like some kind of conservation of energy, right? Here also, you have a domain. You have different phases, different grain boundaries, different interfaces. All of those have some kind of energy. Like every phase has formation energy. Grain boundaries have grain boundary energies. Interfaces have interface energies. So if you can put together a functional, which we call it total free energy functional, then you are going to make a phase field model. Because if you minimize this total free energy, what happens? First of all, here phi is our order parameter. So what phi represent here, phi will take value 1 in the red, which is solid. Will take value 0 at the matrix, which is liquid, blue. And at the interface, there's a smooth transition from 0 to 1. That's just a marker. So if you take a derivative of free energy respect to phi, what happens? Put it equal 0. Take the derivative, put it equal 0. You get the equilibrium condition, right? So, but is solidification an equilibrium phenomena? No, it's a non-equilibrium phenomena, so you need to have a time-dependent equation. So starting with this, let me explain a little bit more. The last term, as you see, a gradient. So this term is related to interface. So you have a finite value for gradient, you put it here. This is interface. How about these terms? What these terms represent? These are the formation energy of solid and liquid. Let me plot it very fast, what you see here. This is liquid. As I mentioned, phi is 0. This is solid, phi is 1. So temperature changes. If you are above the melting temperature, which phase is more stable? Liquid. Liquid has lower energy than the solid. If you decrease the temperature, lower the melting point, solidification will start. So solid is more stable. You are here, liquid is still here. So this basically represents the phase diagram. Okay. The last term could be more complex. I put these equations for you, so okay, something is wrong. Okay, the equation didn't show up. I'm sorry, the equation don't show up. So anyway, how it's going to work is we are going to have two equations. One time-dependent equation for phi, which is coupled to, so we have temperature. We need to have an equation for temperature as well. So temperature will evolve. So it is a heat transfer equation. It's a regular heat transfer equation coupled to phase field. You solve it, and you get these structures. And these are for pure aluminum, pure magnesium. In reality, in industry scale, we usually don't use pure materials. We use alloy systems, right? So what we did was we modified the governing equation. So let me say, those two equations are here. Temperature, heat transfer, phi, phase field. So these two are only good for pure material. But what if we have alloying elements coming? We need to have a diffusion type equation coupled to this, right? So I represent the number of alloying elements. If it's a binary system, I is 1. If it is ternary, questions?
In your previous slide, was that growth of dendrites in supercooled melt?
These are isothermal at melting point. No. These are supercooled, yes. This two first one is exact. Yes.
Along the edge?
Yes, along these 4 edges, yes. You're welcome. So in the cases that we have alloying elements, we have these equations. So one thing is we have developed the computational model, how we solve it. The next step is the numerical analysis. We need to solve partial differential equations which are coupled. In this case, we're lucky because all these equations are second order. In some cases, in solid state, when you have diffusion, so you will end up having Cahn-Hilliard force order equations. So another part of a computational model is to solve equations, okay? So what are the results? Oh, before that, maybe I should say this table. Why actually I put this table? These are the input parameters that we need to provide to these equations. Some of them, you can find it in databases. You can find it in literature based on experiments. But what if you don't have one of these? What if you don't have diffusivity of an alloying element in the liquid? What do you need to do? You can do experiments. It's going to be expensive. It could get very hard to do. You can run some other simulations type. You can run a little bit lower scale simulation, like atomistic scale simulations to determine diffusion coefficients, or many other things like interface properties. So the results. These are the results of alloying elements. So this is the aluminum copper that my colleague were actually working on. And this is a magnesium AZ91. I just put 9% aluminum because this is actually showing color bar shows the concentration of aluminum here. So nice pictures, very good, but are they right? Are the results correct? Okay, are they reliable? So you need to validate your results. This is another step to do. So basically what we did was SDAS is representing secondary dendrite arm spacing. So basically these are the primary arms, 6. So hexagonal closed pack is magnesium. Secondary arms are these small ones, okay? You can get actual average secondary arm spacing from your model. You can compare it to experiment. These are actually believed to control the mechanical properties of cast alloy. So this is why we're actually plotting this. These are the results from 4 different research groups from all over the world, actually. Some of them are from Australia, some of them in Europe, and some in the United States. And these are not linear relationship. These are in log scale. But the point I want to make here, our model, phase field PF model, captures basically the experimental data. We have lots of other actually validation graphs, but this is the one that I wanted to show you today. What are the limits? What are the limits of this model? Does this model see a liquid metal flow effect? No. It wasn't coupled to Navier-Stokes, right? Does it see voids created by solidification shrinkage? No. So this is actually the areas that you have to identify and work on that. And basically, we are working on that. So these are the one coupled with Navier-Stokes. So you see flow, liquid flow velocity from the left coming and changing the size. And it can also rotate the partially solidified dendrites. 3-dimensional simulations is the next step, which I wanted to talk about. So the first part in computational modeling, develop the mathematical models based on physics. The second part is solving those equations. The third part, if you have a big domain, 3-dimensional domain, complex equations, lots of equations, you need supercomputing. Go ahead.
The last page, 2-dimensional simulation?
Yes. Yes, these are all.
What was your boundary condition? Constant area?
These are not periodic boundary conditions, if you're asking for that. These are not periodic boundary conditions. So we have constant values at the boundary.
So you let it contract as it freezes?
Yes. Good question. No. This one doesn't see contraction. It is not.
The solid and the liquid have the same volume?
We have change of density. We have change of diffusion. But basically, as the contraction that you see, and you have to have mechanical constitutive equations, which happens in the next one, which have Navier-Stokes. Okay, so more advanced. So these are the holes in the models that we found, and we have to modify it. And this is what we are doing. So it's now coupled with Navier-Stokes, so it will see that. And basically, the next step for this is to solve very large, arrays of matrices using supercomputers. And this is the largest scale that we simulated. It's 3.6 billion grid points. how long it takes, how many CPU cores we need. So more than 1,000, 8 days. Okay? Then you can have pretty good results. You can have all the details you want. When you compare it, so if I don't tell you that this is an SCM picture, you will not see the difference. So to get good results, you need to include all the features, then it will get very complex. So you need to have a supercomputing to solve. So this was the series of examples I wanted to show for the solidification. The next one is a completely different application, completely different material. Let's go for nuclear reactors. So this is the assembly of nuclear fuel rods. And this is the failed nuclear fuel rod. And you're looking at the surface of this nuclear fuel rod, failed one. So you see here the crack. You see lots of these small lines in this direction. They are hydride precipitates. This layer here is dark gray. It's oxide zirconium. It's called zirconia. So basically the cladding is zirconium alloy, usually called zircaloy. And what is being used as the coolant is water, high pressure water, but it's at high temperature. So it will react with the zirconium. Initially, it will create a very thin oxide layer. It's a tetragonal phase. It's a pretty good phase, actually. But as the oxide scale grows, it will transform to a monoclinic phase, which is not a good one. We get volume expansion. We get lots of cracks. And this is what happens. Another thing is, so that is the oxygen reaction. How about hydrogen? Hydrogen of the water react with the zirconium, will produce hydride precipitates. Why hydride precipitates are bad? They are brittle phases. Cracks come, reaches those phases, grow very fast. Okay? So we don't want any of those. So let's see how phase field model can simulate those phenomena. I'm not going to talk about all those. I'm going to emphasize on the phase transformation part, what we have developed. For example, a model for oxidation of metals, and we applied it to zirconium. What it can predict is how much thickness that layer will become after time of oxidation at different temperatures. It also predicts the stresses generated. Okay, so it is completely coupled to constitutive equations of solid mechanics. What this model cannot predict is the phase transformation happening here. This phase transformation is the key, actually, to completely start and destroy the cladding. Because of the phase transformation, we are going to have volume expansion, lots of cracks. The next one, just one page on hydride precipitate. So hydrogen will react. What happens when hydrogen reacts? This is another model that one of my PhD students, Jake Baer, is working on. He's going to finish this summer, so very close to final results. So here is the hydride precipitates are red, and blue is just zirconium. How we can make a model for this? We have concentration of hydrogen. You see these three orientation of hydrides. These are preferred orientation. Zirconium is a hexagonal closed pack material, so six-fold symmetry, like 60-degree symmetry. Okay, and they tend to accumulate at the basal plane, so these are having 60 degree. So we needed to have 3 order parameters just for orientation. So this is the map of orientation of those precipitates. Okay, what else can this model predict? Generated stresses. These are at gigapascal. So if you have precipitates that are brittle phases, you have fields of stress very high around these precipitates. It's just basically promoting crack to propagate faster and faster. Catastrophic failure could happen. But again, I mentioned that I'm not going to go to the details of oxidation and hydroprecipitation. Let's go back to the phase transformation. Oxygen reacts with zirconium. What crystal structures we can get? This is at very high temperature. We are not concerned with this one. This is the one happens, actually, most of the time. Tetragonal at this high temperature. Then it will transform to monoclinic. These are for pure zirconium. Okay, so we usually have some other materials added. But let's look at this. This is tetragonal monoclinic. These are the atoms, oxygen and zirconium. How we can make a model for this based on phase field model. So we need to know, based on crystallography, how many different ways we can rearrange the atoms here to get to this, just rearrange atoms. So if you know crystallography, it's not going to be that hard to figure that out. 12 different ways in 12 different ways we can rearrange the atoms and get to this. So based on that, how many phase field variables we need? 12. Okay? So we use, again, we need to build a total free energy functional, right? So starting from the same step, instead of having one term, we have two terms now because we are in solid state. At least we are going to have elastic strain energy developed, right? So this was very similar to the previous one for solidification. Now we have this added. So this is the chemical free energy, eta 1 to eta n. N is 12 here. So I put it here, n, because this can be applied to any kind of phase transformation like this. This kind of phase transformation is called martensitic phase transformation. It could happen in all these steels, in titanium alloys, in zirconium alloys, and many others. So this model actually can be applied to other alloy system and study those. And these terms that have gradients, they are just representing the interface of the precipitates and the matrix, or interface between the precipitates. So this is the chemical free energy. We need to put together this functional here, right? This is called what? This is called, a little bit more detail, local specific free energy. We call it Landau polynomial. We have actually a complete paper on this, how to make this for different systems. So for this case, we are going to have eta 1 to eta n. So A, B, C are crystallographic information. So you can actually get it from crystallography. The last part is important. Last part is the difference in the free energy formation of phases you have. Matrix and the transformed phase, okay? So if you have that, you can have it from thermodynamic calculations from phase diagrams. You can calculate it from density functional theory. It could be related to cohesive energy, also from molecular dynamics, atomistic simulations. The last part, elastic strain energy, is also a routine procedure for this, considering a small strain effect. And you're probably familiar with this. This is CIJK, CIJKL is just 81 constants, elastic constants matrix. So you can get it actually from experiments. You can actually calculate it from lower scale modeling. The question here is how many different equations we have to solve. We have 12 order parameters. How many equations here in 3D? In each direction we have one, so 3 plus 12, 15 equations that you need to solve. So basically we started again with 2D, so make it a little bit more simpler. This is the 2D example showing twin phase transformation from blue, which is zirconia, to monoclinic. And these are stress fields. And we quantitatively validated our simulation. We measured the size, the distance, the volume fraction, compared it to experiments. So these are quantitative models. What else we did? We ran three-dimensional simulations for free surfaces. Why? Because cladding is in contact with water. So that surface you can mechanically actually corrugate or deform. It's almost a free surface. So what happens if we run it in 3D simulations and we have a free surface at the top? We get corrugations actually. These are corrugation at the surface that we predicted, and these are validations from AFM micrograph, atom force microscopy. So we can actually quantitatively predict where the cracks are going to happen. Cracks are going to happen here. Okay. In reality, we have polycrystalline systems. Those that I showed you, they were just single crystal. So for polycrystalline, I didn't put the equations. They're going to get really messy here. So grain boundaries, you need to have all the grain boundary energy information transferred to this model, and we did it already, and these are the patterns. While we were doing this simulations, we found that zirconia has many other applications. In 2013, I found a paper published in Science that shows that zirconia has this property which is called shape memory. What is shape memory? So look at the this is a small filament. So at a smaller scales, if you have made a filament, if you apply pressure on that, you deform it, applying load. If you heat it up, it will go back to the initial shape. It is called shape memory, so it remembers its initial shape. So we didn't actually build a model based on this, but we wanted to know if our model can predict this. And the answer is yes, our model can predict this. So this is what we have. We have a polycrystalline tetragonal. We apply loading, go to transformation, plasticity, unloading. Here, we get transformed twin phases. But it's not going to go back to the initial shape, so by itself, you need to heat it and cool it, and you can get the initial microstructure phase. So basically, you can predict, but again, what are the limitations? What are the limitations of this model? The limitations is this model cannot see the defects, dislocations, deformation mechanism, or failure mechanism. So it means if you load and unload, heat and cool 100 times, you get a different pass. This is called hysteresis. Do you get a different hysteresis loop? The answer is no, because you don't see any defects or dislocations. So at this moment, actually, it was 2014, I decided that I should go to a different direction. And we did a heavy literature review to see if there are anything on deformation mechanisms or failure mechanisms of zirconia, and there weren't any. So we started a different line of research based on that, just finding something that's important. And we are going after molecular dynamic simulations, atomistic simulations. So here you see a filament, right? I know that the cross-section is not circular, but it will do the work. How many atoms we need? More than 1.5 million, okay? I don't want you to follow all the data I put here. I'll put like colors here. So the first three shows only dislocation happened. What is dislocation? Line defect, like a slip. The next four, dislocation and phase transformation, and last one, phase transition. So we found a regime that changes the deformation mechanism, going from dislocation to complete phase transformation. And the reason was the direction of loading. Basically, it's an orientation-dependent problem we are looking at. So we have actually asked the research group in Dr. Shu's group in MIT to do a little bit. Actually, we are going to ask them to do a little bit of research in this to see if they can find it out in their experiments as well or not. So just make it a little bit more exciting, we put some movies for these atomistic simulations, and put a little bit of information on supercomputing. What do you need actually to simulate more than 1.5 million atoms? Basically, you need 256 CPU cores for 25 hours. But again, these are the total simulation time 0.4 nanoseconds. So we need to transfer this to a phase field model. Phase field model can run for seconds simulation time. So these can give us some mechanism information about the deformation mechanism and failure mechanism. This is a dislocation case. This is the both dislocation and phase transformation. The last one is complete phase transformation. These are the examples. So lastly, I will go through this really fast. A phase field crystal model. So a little bit different than the previous one. How they are different? The free energy functionals are different. As I mentioned, if we have two phases, the phase field variable takes this form. A constant, a smooth transition to another phase, right? The phase field crystal will produce a periodic form. Why periodic form is good? Metals have periodic crystal structures, right? So they can predict metallic crystal structure. But the difference is very important. It will computationally will be very complex because the gradient term. This is the phase field model. First order gradient in the free energy. This has fourth order gradient, and this is actually the simplest phase field crystal. We are using eighth order gradient. How it is related to lower scale models? How it is related to electronic structures or atomistic scale? Do you have a question?
I didn't quite catch what you were plotting in the previous slide.
Ada.
What's the scale on lower? Is that the nanoscale?
This is actually in the nanoscale. It's very small. Oh, these are density of atoms, density peaks of atoms.
So it's not the traditional phase field model?
No, this one is not. This one is the phase field crystal, the one that is periodic. This one, which has a constant values in both phases, is the traditional phase field. So since I'm here, this eta could be concentration or any other kind of orientation field variables. Here, phi is density field in phase field crystal. It's always density. It comes from density functional theory, and basically it's free energy functional derived from density functional theory. So this is a simple version of free energy functional of density functional theory. You probably have seen this formulation somewhere. This is the correlation function in K space or Fourier space. And this is the backward Fourier transform. Okay, so it will become a real space. But this is discrete, so I'm going to talk about it very fast. But how we can make an approximation of this, if we use a polynomial of 8th order replacing the correlation function, representing the interatomic actually relationships, in real space it will be 8th order. So this is why we get high order gradients. In Fourier space, it's just a polynomial of 8th order. In real space, 8th order. And replace this here, you get the phase field crystal free energy. Again, we have a free energy. And then we can go and find our evolution equations. But why this is a game changer? Because it's based on density functional theory. Every single parameters in this could be calculated based on a structure factor of a material. What is the structure factor of a material? It's just a fingerprint of the material. Okay? Fingerprint of material at different temperatures, they are going to be different. But in a particular temperature, this is a structure factor. It's only for one material. It's a fingerprint. Based on this, so this is the first peak, shows the first nearest neighbor effect. So we have an atom. We have first nearing atom. So this is this effect. This is the second nearest neighbor. So with 8th order, we can represent second nearest neighbor interatomic potentials. So it is connected through density to phase field. How we can determine the structure factors? That is the question. It's not an easy task to do. This is why we have a project on this. We need to provide data for this model. And we use, so this MEM stands for Modified Embedded Atom Method, and MD is Molecular Dynamic Simulations. You can get very accurate prediction of structure factors of materials through this. You get this, you find your model parameters, run simulations. What do you get out of your simulations? This is a large scale simulation in 3D, but I'm not going to show you this. Let's go to a little bit more detail. Starting from liquid, go to solid, and going through solid state phase transformation. Let's concentrate on the corners of this, see what is happening, and what we can see from this. Again, this is not possible to simulate with MD simulations. These are in seconds. Molecular dynamics is in femtosecond, so diffusive time scale. These are the starting point of solidification. We get nucleation of solid phases. Then we get grain boundaries are forming. Still, we have a little bit of liquid. And this stage, we get defects and initial grains at the melting point. These are melting point. So we simulated this, but other models cannot do that. You have to transfer all this information to a solid state model. You don't need to do that. Don't stop the simulation. Cool it down. What's happening? So we cool it down. It goes forward, and so this is solid state. It goes forward and become this. So we get from here to here, we get grain growth, we get movement of dislocations. So basically, we can simulate elasticity, plasticity, dislocation formation, grain boundary formation, and many different things. This is a density field, similar to DFT. You can deform it. You can get elastic properties out of it. Okay. What else this model can predict? This model can predict many other things, actually. This is, I guess, the first model can predict quasi-crystalline tenfold symmetry. And we actually didn't build a model for this, But apparently in one part of our phase diagram, we can simulate this kind of materials that they have 10-fold symmetries. Okay? As far as we have some kind of symmetry, the model will detect it. Okay? So with this, I should go to conclusion. So very few, to one slide on just recapping what I just told you. The first one was on solidification. Again, lots of application, not just for metals. The crystallization happens in polymers, in semi-crystalline polymers, and some other type materials as well. So it will contribute, these particular cases that I showed will contribute to energy efficiency and safety of vehicles because they were lightweight. I also, until now, we focus on zirconium alloys. We are starting to look at the interaction between the fuel and the cladding, and it's actually going to be some of our future research, and at the end, the phase fill model. So these were the 3 different directions I talked to you about. I have 4 other projects that I didn't have time to talk about today. So with this, I wanted to go back to this slide. The main point is we can use computational modeling to study different features of materials, different materials for different applications, but the most important thing is to understand which scale of modeling we have to use, how we verify and validate. This is just the map for additive manufacturing. We submitted a recent proposal to NSF. So we have lots of modeling tools we can use for studying additive manufacturing. Every one of them need to be actually validated and verified. So it is a very good opportunity to integrate computational modeling and experiments. And lastly, and most importantly, education. Education in computational material science is lacking. And this is why actually this is the first course I developed, and it's being taught in, I guess, 7 other universities in the United States. It is ICME, Integrated Computational Materials Engineering. And this is the poster actually we presented in one of the education conferences. Let me make it a little bit bigger. This course covers 5 different models. Electronic scale, atomistic scale, 2 mesoscale, phase field, dislocation dynamics, and finite element. You may be familiar with using abacus, ANSYS, COMSOL. These are here. The first thing that we do in this course is we introduce different type of models, what data and information they can provide, and how actually we can pass data between these 2 different length scales. It is really important the data that you're providing here may be used directly actually in macro scale, like elastic constants. Okay, so with this, thank you so much for listening, and I'll be happy to answer your questions. Very good question. Yes, so I didn't show you that slide. You need to do size scale effect study. Okay? So let me see if I can go back to that slide really fast. Okay, so why we chose 1.5 million? Why not 100, right? Why not 100,000? Or why not 10 million? First of all, one of the reasons is we cannot usually go more than 5 million at a time because then we cannot visualize it. We do not have a computer available to do that. So we stick with less than 5 million. And it's going to be a really huge supercomputing needing for that. But if you go less than like 800,000 atoms for this case, the behavior will change. The behavior will change. So we wanted to make it as close as to experiments. If you remember, the experiment filament size was 1 micron. Okay? This is about 25 nanometer. So if we make it like less than 10 nanometer, less than 5 nanometer, you know, these scales here, these 2, it's going to behave completely differently. So this is why, yes, we need to do size scale effect studies as well.
Are you essentially nucleating a dislocation on that slip line? Is that what's going
For this one, yes. So we initially don't have any nucleation or anything, any defects or nothing. This is a perfect single crystal, actually, column. And when you deform it, it will happen by itself. So we are not initiating any nucleation ourselves.
Can you see that the dislocation nucleates somewhere, or does the slip plane move throughout evenly?
We have actually identified the nucleation of dislocation first. So if we have actually zoomed in some, in this actually plane, we initially see dislocation, but eventually it will look like a complete slip.
So what sort of boundary conditions do you put on it? Is it
Good question. So we have.
held rigidly at the top and bottom and free on the sides?
So this is basically rigid at the bottom. We are deforming it from the top. And as you can see, it's not a periodic boundary condition. It's free surface, like the filament that they produced in their experiment.
Well, the sheet memory effect is really interesting. Is that essentially the same as nitinol?
Nickel titanium, yes. Martensitic phase transformation, yes.
Do people use that in zirconia at all?
Not zirconia. For the actuator applications, no, it's just a concept for now. Just experimentally, yes. It's not in application, like in industry scale. It needs much more actually research in this before it goes to that stage.
Have you also looked into nucleation before then applying the basic model to see how nucleation was?
Very important, especially for like solidification, crystallization. It's very important to have a really good nucleation criteria. So we are looking at right now for a couple of alloys, aluminum, copper, and magnesium aluminum, especially these two because of the funding we have. So we're in the earliest stage of solidification. We're looking at nucleation, yes. But for those that I showed you, those are thermally fluctuation nucleation based on the classical nucleation theory.
Was that last solidification, the phase crystal model, was that 2D or 3D?
Phase field, that's the 3D, is just the cross section so you could see. It's the three-dimension.
Three-dimensional model.
Yes, it has a thickness in Z direction. Yes?
There's a lot of work going on here on ice. Have you also looked into water, crystallization of water?
I didn't brought that picture, yes. It's very similar to magnesium, actually. It's somehow six-fold symmetry. And Go ahead.
Classic problem in machine learning is if you have a model with too many parameters, then it doesn't generalize well, doesn't fix the data well. And if it has too few parameters, then it's not complex enough to fit the data, but it can generalize well. So I'm just wondering, given your multi-scale all the way from atom to material, if I come to you and say, okay, you proved for zirconium, I can predict this. And now I say, will it work for hafnium? Which is similar but different. How do these generalize given known parameters of atoms, chemistry, alloys, so forth?
Yeah. Very good question. So the question is, can we extend the model and use it for other material? And basically, if we're looking for the deformation mechanisms, or we're looking at like fracture mechanisms, the answer is no, because it has to be done separately. But if you look at a little bit higher length scale, like a phase field model, so larger than this, yes. For example, if I go back to that phase transformation example, just the equations I mentioned, those can be applied. Sorry. If I go back, okay, good. So here, I mentioned that this is a general model. I said, depending on the crystallography, you could change this crystallography from, this is zirconia, but let's assume that you have a third generation advanced high strength steels that goes through martensitic phase transformation. How many different ways you can actually rearrange the atoms? We know that it's 24. So you need to have 24 ADAs. So this is how we can actually adapt the model. But again, basically, if you want to fundamentally study the mechanism of deformation or fracture mechanics. No, it has to be done separately because for molecular dynamics, the interatomic potentials are completely different. So, but in phase field, we have, if I go back to I guess if I go to the first page, some of them that I didn't talk about, some of the, some of the models that I didn't talk about today could be a really good example of those. For example, this one. This one is a crystallization of a semi-crystalline polymer. How different is this model than this one? That is the question, right? It's basically not that different. The interface properties, the formation energies, and the interface anisotropy will produce this kind of crystalline structure. For the semi-crystalline polymers, this is the magnesium, by the way. So it could be extended to even completely different type of materials, phase field model. But if you go to molecular dynamics, it's not. You need different interatomic potentials. The mechanisms are completely different.
Here's a question that you may know the answer to with this methodology. Many steels become brittle as you cool. Can you tell me under the conditions given steel, virgin steel will become brittle?
By phase field model? By MD simulations, yes. By MD simulations, yes. By molecular dynamics, atomistic simulations, if we have the right interatomic potential. If we have the interatomic potentials for atomistic simulations, we can see actually we can study failure mechanisms. We can see transformation from ductile to brittle. We can actually see the difference, the jumping in the stress strain curves. So MD simulations is one of the primary methods to use actually to capture mechanical properties, primarily for single crystals. Then we can extend it, depending on superconducting, to polycrystalline materials. But atomistic simulation, molecular dynamics is the answer to your question. But when you go to the actual macrostructure, then the question is, can we predict the size, shape of those transform? We need to transfer the data and information from MD simulations to the phase field model. Similar to the model that I showed you for zirconia, there are lots of different things that we transferred from lower scale models to that, like the transition between dislocation to fully transformed. It's not going to be captured by phase field, but it could be, actually it can be captured by molecular dynamic simulations.
So that's what raised the question when I was looking at your simulation on zirconia.
Mm-hmm.
You loaded it and you got a slip plane activated, and presumably that's some solidification, nucleation, and propagation.
Yes.
Well, why didn't it fracture?
We have cases that fractured.
Simply fractures.
Yeah. I don't have actually the fracture case here. So that is the direction dependency. So in some directions, you're going to activate the slip lane. It's basically that. And if I go back to that example again, so you will see, for example, here, where is this? Okay. This one, this one, if you look at this, the loading direction is 0, 0, 1. If we change the loading direction, it will change. We have cases that have fractured, but we have not applied enough load. We just wanted to study the initial. The fracture study is the next. Definitely, it's in a step in our study. So here, basically, if I go back to this table, the loading directions that we presented here and the amount of applied pressure, is it enough to create fracture? That is the question. We didn't go that far. We just wanted to see the transition between dislocation and fracture. In some cases, we did see fracture. I don't have actually the results now. These are actually the results that we got like a couple of months ago. So these are also very new, not published yet. Thank you very much.